Alright, welcome back. So today we're going to continue talking about iterated integrals and a few more applications. First we're going to talk about some techniques that can be used if you want to or need to change the order of integration of an iterated integral. Maybe it comes to you in the order dy dx, but you need to change it to the order dx dy. Perhaps one of those orders is not possible to calculate, and you need to change it to a different order in order to make it possible to actually calculate the integral. And we'll talk about how to do that. Second, we're going to use iterated integrals to calculate a couple of things. First, we're going to use it as a way of calculating the areas of two-dimensional regions. And three, we're going to use it to calculate the average value of a function, just the same way that we found average value of a function back in Calculus 2. Okay, so let's consider the following problem. Someone asked me to evaluate the integral from 0 to 1, integral from y to 1 of e to the x squared dx dy. But the immediate problem is that e to the x squared doesn't have an antiderivative with respect to x. Respect to x. So as soon as I get in and I try and calculate this innermost integral, I'm going to run into trouble right away because I'm not going to be able to find an antiderivative of e to the x squared. So one idea in situations like this, where you are immediately just blocked and you cannot calculate this first antiderivative, is to try and see if you will be a little bit more lucky if you change the order of integration from dx dy to dy dx. And that's our idea. Change the order of integration. Which means that we are going to need a pretty good idea and a drawing of what the region of integration looks like. Let's draw the region R. So let's analyze these limits of integration and let's work backward from the limits to the region R. Now, the innermost limits of integration tell me that x equals 1 is on the right side of the region, and x equals y is on the left side of the region. That is the analysis that we used to set up those inner limits of integration. The upper limit of integration was equal to the right-hand function, in the case that x was the first limit. Now, if we look at the limits of integration on the outside, that tells us that y equals 1 is the largest y-coordinate, and the lower limit of integration on the outside, y equals 0, is the smallest y-coordinate in the region. So let's set up some axes and let's see if we can draw a region which satisfies those conditions. So first, I'm going to draw the graph of y equals x, which is a diagonal line going through the origin. Except I can't draw the line all the way into quadrant number 3 because y equals 0 is the smallest y-coordinate. So I should stop drawing the line as soon as it hits y-coordinate 0. And likewise, I should stop drawing the line as soon as it hits y-coordinate 1. This is the smallest and the largest y-coordinate in the region. Then it says x equals 1 bounds the region on the right. So I'll draw the vertical line x equals 1 from the topmost y value to the bottommost y value. And so that is the region R. So this time I want to set up the limits of integration in the order where y comes first and x comes last. Which means that instead of thinking about left and right boundaries, I need to think about top and bottom boundaries. For example, here on the top, the region is bounded by the function y equals x. And on the bottom, the region is bounded by the function y equals 0. And so the y limits of integration would go from 0 to x. Now I need to consider what is the smallest x value and what is the largest x value in this region. Well, at the smallest, x is equal to 0 here at the origin. And at the largest, x is equal to 1 here on the right side. So the x limits of integration will go from 0 up to 1. So let's try and integrate our function e to the x squared with the opposite order of integration, starting with y, progressing to x. Alright, well now x is constant. With respect to y, x is constant. So, e to the x squared, if x is constant, that's just a number. So let's integrate e to the x squared with respect to y. Because it's just a number, the antiderivative with respect to y can be found just by multiplying by y. And then we can plug in the upper and lower limits, y equals 0 and y equals x. Now if I plug in y equals x, I get x e to the x squared, and if I plug in y equals 0, the entire quantity vanishes. So that leaves me with the integral from 0 to 1, x e to the x squared dx. And all of a sudden, because of that extra factor of x, this integral, which was originally impossible, has suddenly become possible. Because we can use a u substitution. We can sub in u equals x squared, so that du is equal to 2x dx. And so we can integrate from x equals 0 to x equals 1 of 1/2 e to the u du, which is 1/2 e to the u, evaluated as x goes from 0 to 1, which is 1/2 e to the x squared, evaluated as x goes from 0 to 1, which is equal to 1/2 e minus 1/2 e to the first power, which is equal to 1. An absolutely gorgeous technique. An integral which used to be absolutely out of control has become manageable simply by drawing the region, turning your head, and instead of looking at the limits from left and right perspective, you look at the limits from the bottom to top perspective. And now you have a possible integral. That's wild. Okay, so now that we have discussed this technique for changing limits of integration and changing the order, let's talk about a couple of applications of double integrals to a variety of other situations. We've already talked about things like the volume under a surface or the volume between two surfaces, but actually double integrals can also be used to calculate two-dimensional quantities as well. For example, if you want the area of a region R, then all you have to do is integrate 1 over that region R. And just for a vague explanation of why that's true, if I draw the region R down here at the xy plane, and I consider a function of height 1, of constant height 1, then the volume is going to be equal to area of R times the height of 1. Now the volume can be found by integrating the height function 1 over the region. And so this is how we get this sort of equation. A volume can be thought of as an area. The volume with a height of 1 is equal in value to the area at the base. I know it's a really quick explanation. It's not meant to be too deep. It's just something that might help you think about it, perhaps. Now, here's how we're going to use this calculation. The average value of a function, on average, what kind of outputs are you seeing from this function over the region R? This can be found by calculating the double integral of the function over the region R and then dividing by the area of the region R. So this is precisely the same as average value. Here's our thought bubble. Average value in single variable could be found by taking the integral from a to b of a function and dividing it by the length of the interval by the size of the line segment stretching from a to b. And so what we're doing here is simply the two-dimensional version of this. We're still integrating the function and dividing. Previously, we were dividing by a one-dimensional length. Now we're dividing by a two-dimensional area. So let's consider the following example problem. Let's let R be the right triangle with vertices 0, 0, 3, 0, and 0, 3. Let's find the average value of the function f of xy equals x plus y over the region R. Now I've already set up a few things here just for the sake of saving a little time and cutting to the chase. I've gone ahead and drawn the region R, this right triangle, with 0, 0, 3, 0, and 0, 3 as its vertices. And I've just gone ahead and found the equation of the line, which stretches from 0, 3 down to 3, 0, which is y equals negative x plus 3. Now because this region is triangular, we could find its area by integrating the constant function 1 over r, but it's probably overkill because this is just a triangle. So we can find its area by using the old-fashioned geometric formula 1/2 base times height, which for a base of 3 and a height of 3 gives us 9/2. So what really remains for us to do is to integrate the given function over the region R. And I have personally chosen to use the limits in the order dy dx, but there's absolutely nothing at all that's stopping you from using the limits in the order dx dy. It just seemed to me like it might save me the step of having to solve this equation in particular for x if I leave it in this format. So let's go ahead and let's calculate the integral of our function y plus x over the region where y goes from 0 to negative x plus 3 and x goes from 0 to 3. Now based on that, let's go ahead and find the partial integral of y plus x with respect to y. Using the power rule, we have y squared over 2 from y and x times y from x, evaluated as y goes from 0 to negative x plus 3. Let's plug that in, and we get the integral from 0 to 3 of negative x plus 3 quantity squared over 2 plus x times negative x plus 3. And if I plug in y equals 0 to either one of these terms, they both vanish and contribute nothing to this definite integral. Now let's do a little bit of simplification before we carry on with the next iteration, the outermost integral. We have the integral from 0 to 3. And let's go ahead and let's find this square. So we have negative x squared over 2. We have negative x times 3 times 2 over 2. We have 3 squared over 2. And then we can distribute through x, negative x squared plus 3x, which is very nice because we get to combine a lot of like terms. X squared half, take away x squared, negative x squared half. Negative 3x plus 3x vanishes, and we have plus 9. Then we have one more loop to go. We have negative x cubed over 6 plus 9x, evaluated as x goes from 0 to 3. Now plugging in x equals 0 will again cause both of these terms to vanish. So we have 3 cubed, negative 3 cubed, negative 27 over 6, plus 27 from 9 times 3. This can be cleaned up a bit as well, but you know what? I'm not sure if it's worth the time. So I'm just going to leave my final answer for the double integral in this format. But be careful, because what we have calculated as of this moment is not equal to the average value that we were asked for at the beginning of the problem. We have to be careful and remember that it still remains to take this integral value and divide it by the area of the region, the area of the triangular region R, which was at 9 over 2. This number would be the final answer for this question.